So yeah, our speaker this week is Anta-Clarisse Sarr, and unless she surprises us, I believe she will be talking about the Neogene South Asian monsoon rainfall and wind histories diverged due to topographic effects. So this is a paper that was sent out earlier that appeared in Nature Geoscience. And so I just wanted to give a very high-level overview of this work, just to give us a context on what she will talk about on Wednesday. Most likely she will give more details and a little bit more scientific context, as this is not particularly my background. I just wanted to share the high-level interpretation that I was able to get from the paper, just so we can have a little bit better understanding of what the work is entailing. So a little bit background on our speaker. She's currently a postdoc at CEREGE. Perhaps there's a pronunciation for that, but I don't dare try it myself. Her research interests are paleoclimate modeling for geodynamics, geography, and climate applications. And also she's looked at the connection between the mantle biosphere and orbital variability with climate. She received some degrees from her PhD and master's from Grenoble Alpes University in France, and also master's at UNILASALLE, also in France. So let me just try to move this thing out of the way. So the South Asian monsoon, which is the focus of our talk, of her talk this Wednesday, is essentially an annual cycle of, basically we know it as an annual cycle of heavy rainfalls during the summer in India. And the formation of it during the year is based off of the intertropical convergence zone, essentially the high winds near the equator, which is formed from a global zone of low pressure over warm waters. And so in late winter, at the end of the winter, the ITCZ shifts north as the land warms. And then this brings trade winds coming in from the equator. And so these trade winds carry with them a lot of moisture and warmer temperatures. So that heats up the land and then dumps a whole bunch of water onto the land, the continent of India, from the land of India. And in the cooler months, as the land cools, the winds reverse direction, and it brings along a much drier air during the winter that comes from the Himalayas. So this is a very important seasonal phenomenon. It's a primary mechanism for freshwater delivery for India, and economically, it's extremely important, because since agriculture accounts for 1/6 of the GDP of India, and so these rainfalls, even though they can be hazardous and bring flooding, they're very important for maintaining the production of agriculture. But in terms of scientific understanding, the main objective of this work is to determine what drove the onset of the SAM, because it hasn't been around forever. As the continent shifts, and as the topography changes due to collisions of plates, of continental plates, the global circulation will change. And so the main motivation is they want to understand, how did the SAM form, and how did it respond to changing climate and geographic landscapes? So this can actually be important for us in the future, because our climate is changing as well. So it would be interesting to see if we can understand what are the changing drivers of SAM onset. We could potentially get a better understanding of how these rainfall patterns could change in the future, as topography will change as well, but that's a much, much longer time scale. And so that's the main motivation. And the specific motivation of this work is they want to be able to reconcile conflicting interpretations of monsoon proxies using paleoclimate simulations with Earth system models. So with regards to the conflicting interpretations, basically there are different independent lines of evidence that all kind of tell different pictures on when the SAM formed. So there are isotopic and botanical records that suggest strong rainfall seasonality started around at least the Paleogene, so 66 to 23 million years ago. But then if you look at the sediment archives of the Himalayan foothills, they suggest a little bit later, intensification of rainfall around 25 to 20 million years ago, peaking at 15 million years ago. And actually, if you read a lot of the work on the onset of SAM, they do tend to suggest that the formation of the Tibetan Plateau and the Himalayan mountains, that's the key driver form that basically started the whole seasonal cycle of the SAM. So keep that in mind, because she will look at that in particular, that effect in particular. And finally, there are IODP sediment samples. So basically samples obtained from cruises over certain areas in the Western Arabian Sea. And there they indicate an onset closer to late Miocene, so about 13 million years, associated with strong wind-driven upwelling, basically upwelling in the ocean, which we'll talk about more later, and high primary production, photosynthesis by algae. So a term that we'll look at several times here is primary production. Basically, you can just think of this as the production of organic elements and chemicals by algae in the ocean during photosynthesis. So the strategy here is they wanted to use Earth system modeling, specifically IPSL CM5A2, combined with an offline biogeochemistry component to kind of look at the interaction between atmospheric circulation, the geographic distribution of continents, and then how that will affect ocean circulation. So this is just kind of showing how the spatial domain is discretized into different grid cells. So in this work, Sarr et al., they performed two sets of investigations for studying the formation of the SAM. So the first, basically the first strategy is they wanted to use realistic land-sea configurations during the early Miocene and late Miocene. So narrow it down to the distribution of the continents in the EM and the LM and see how they affect the simulations of atmospheric circulation. And then a little bit more detailed work in the second half of the paper is they systematically add and subtract key geographic features to investigate the sensitivity of the simulations. So specifically things like the Himalayas and the Anatolian Iran orogeny. You want to see how certain mountain ranges will affect the atmospheric patterns, atmospheric circulation patterns. And they'll use the simulation outputs to determine which configurations lead to the configurations that are closest to what we observe today. So this is kind of just showing the distribution of continents during the early Miocene and the late Miocene. And then within this distribution, we're focusing on the paleoclimate here in the Indian Ocean. And so when they look specifically at the LM and the EM configurations, what they see is that the Somali jet, which is essentially just a very persistent jet of strong winds, which is what we see today. Because it essentially starts from the Somalia area and then flows over towards India. The Somali jet only forms in the late Miocene with this configuration of land here. And with this formation of the Somali jet, they're going to have much stronger upwelling, which is shown in these blue hatched regions. Whereas in the early Miocene, you have a very, very weak Somali jet. So not enough to start churning the ocean waters to get the upwelling that they'll see in the biological samples. So the key thing is that the strength of the jet is key to the strength of the upwelling and the nutrient delivery. So let's look at that in more detail. So over in the Western Indian Ocean, what they wanted to do was they had an offline ocean biogeochemistry component that is basically hooked on to these Earth system models. And so they're able to simulate the change in the primary production. So if you recall, the primary production is just the outputs of photosynthesis by algae in the oceans. So the higher the primary production, you can just essentially think of it as more algae is in the euphotic zone. It's in the zone where sunlight is still penetrating the ocean. So you have much more plant life, algae activity. And so that's like a key driver to saying that there's a bunch of nutrients in those layers of the ocean. And so during the late Miocene, you have much higher productivity. And if you look at the depth distribution of the productivity, you can see that in the late Miocene, shallow layers, as opposed to the early Miocene, where you get a little bit of peak of productivity right around 80 meters, but then it basically attenuates as you get deeper, and you don't get very much production in the shallower layers. So this graph is essentially just saying that you have a lot of stuff going on in the late Miocene, high production, lots of algae, lots of photosynthesis. And so what's driving all this photosynthesis, all this nutrition in the ocean? It's essentially Ekman transport. So just a quick background over Ekman transport. You probably have heard of this term or have learned about this term in introductory climate courses, or maybe atmospheric dynamics if you've taken that. But the basic concept is that as you get a wind flow, as the wind blows, let's say parallel to a coastline, it will generate friction stress on the surface of the ocean. So as the wind flows, there's friction, and the wind will pull the very top surface of the water along with it. So that will start flowing in one direction. But if you remember the Coriolis force, basically motion of any object on a rotating reference frame, because of the Coriolis force, as the wind drags the ocean along, the ocean will then start to curve its trajectory. And so the net effect of this Coriolis force is that the surface water will actually move at a 90-degree angle to the wind direction, so perpendicular to the wind direction. So along the coastline, you have wind blowing along the coastline. The ocean moves 90 degrees. And so you get a movement of water away from the coastline. So water is evacuating the coastline, it's moving away, and you have conservation of mass. So something has to take place of the water that's moving away from the coastline. And so that water has to come from deeper in the ocean. And so then you get upwelling. So this upwelling is the key point here, because as you get stronger winds, you get more mass transport, more upwelling, and this upwelling is going to bring nutrition from the ocean depths. So you can see that in their simulations here. Primary productivity became strongly seasonal in the late Miocene. So if you look at the months of primary production at 100 meters depth, you can see you have a very strong seasonal pattern where it peaks in August and September. And if you look at the nutrition limitation, you can see that you basically just have more nutrition during those months where production peaks. And the reason that you have a lot of nutrition is because the mean vertical velocity at 80 meters depth peaks right in the few months before August and September. So it peaks around June, July. So you have vertical advection in the ocean that's driven by the Ekman transport and the wind-driven convective mixing. And as we saw before, this whole thing is basically triggered by the strong Somali jet southwestern monsoon winds. So we can look at this a little bit in more detail in these plots here. Let's look at the bottom plot first. This bottom plot is showing wind speed. So you can see in the late Miocene here, you have much stronger wind speeds right off the Arabian Peninsula and the Oman coast, whereas in the early Miocene, you have very, very weak winds. So this is a weak Somali jet. This is the strong Somali jet. And what this leads to is that you get very strong upwelling velocity, very high vertical velocities in the ocean right off the coast of the peninsula. So you have stronger winds, more upwelling, more nutrition availability in the oceans. So again, the reason that they were looking at that was because they wanted to look at, when did what essentially drove the formation of the South Asian monsoon. And one of the key pieces of evidence were the biological records that kind of suggested strong upwelling. So the upwelling was the first piece of evidence that they wanted to look at. And now they wanted to do a more systematic investigation where they wanted to look at the impact of 3 specific paleogeographic features on the SAM development. First, they wanted to look at the rise of the complex orogen extending from the Anatolian to the Iranian plateau. So basically the Anatolia-Iran orogeny, where there's a very high mountain range near the Arabian Peninsula. Also, they wanted to look at the uplift of the East African highlands and also the Himalaya-Tibetan Plateau complex. And also just in general, the presence of land in the Eastern Arabian Peninsula. How did that affect circulation patterns? So if you want to look at what that looks like in terms of actual model inputs. So here we are in the late Miocene. NOAIO is removal of the Anatolia-Iran orogen. So basically, if you look at this color bar, deep blue is a negative. So in this configuration, they basically remove all the mountains in this area, and they want to see, okay, now what's the effect? In no EEP, that's essentially equivalent to submerging the Eastern Arabian Peninsula. They just remove this whole peninsula altogether and then see what's the effect. And finally, here in no EAHR, they get rid of all the East African highlands and then see what's the effect. So first, removal of the Anatolia-Iran orogen. Basically, what you see is you get a significant reduction in wind strength north of 10 north. So you can see here, compared to some of the other LM simulations, you can see we have a little bit weaker wind speeds. And if you look at the upwelling velocity along the Oman coast, which is right around here, basically showing here, you can see that you have a slight decrease in the upwelling velocity. So there is an effect, and it'll become a little bit more clear what that effect is later. But the really big effect here is that if you submerge the Eastern Arabian Peninsula, basically you take away this whole piece of land as if it never existed, then what happens, and what you can see is that the upwelling velocity drops significantly. So it essentially looks just like the early Miocene simulations. The upwelling velocity, you see there are no blue squares here, where that's what they were simulating in the late Miocene. So you get rid of this land, you get rid of the upwelling. So that's basically the key solution here, the key result here. And what it also does is that it suppresses the westward extension of the Himalaya-Tibetan Plateau low pressure anomaly. And we'll look at this a little bit more in detail later. Significantly reduced wind speed and stress. And that basically, we already saw that earlier. And finally, they looked at reducing topography in the East African highlands. So the main effect here for the East African highlands, which is this mountain range here in East Africa, what it does is that it basically causes the if you look at the simulations without the East African highlands, you see that the wind flow just basically kind of has more of a eastward trend. Like the wind basically keeps flowing towards the African continent. But if you put the highlands back in, then it causes the wind direction to kind of bend as it crosses the equator, and then it bends back towards the Indian Ocean. So that looks a little bit more like the Somali jet that we want to see. So there is definitely an important factor here with East African highlands. It's causing the initiation of the bend of the winds towards the Indian Ocean. And so they also looked at changes in the early Miocene. And so here, I think the main focus of these simulations was to see what is the effect of the Himalayan Tibetan Plateau. So, as I mentioned earlier, I mentioned that one of the main hypotheses that says that the main hypotheses for driving the formation of the South Asian monsoon was that the formation of the Himalayan mountains, you get this big topographic feature, and that's essentially what's causing the seasonal cycle of rainfall. And so they wanted to see, okay, does that actually play out if they simulate that in the early Miocene? So there are 3 simulations: increase of the East African highlands, again, similar to what they looked at in the late Miocene, uplift of the Himalaya Tibetan Plateau, and then essentially taking the Himalayan topography that it is today and then increasing it a little bit more just to see what the effect is. So so first with the East African highland topography, similar to with the late Miocene simulation, the main effects of the East African highlands is that it causes the wind to bend towards the Indian Ocean. So it causes the cross-equatorial flow to bend northwards. So it essentially preconditions the formation of the Somali jet. And then that itself will influence the upwelling off the Oman coast. And the interesting thing is that the uplift of the Himalaya Tibetan Plateau actually has very minimal impact on the atmosphere-ocean interactions. So if you look at the wind patterns with or without the Himalayan plateau, they essentially look the same in the early Miocene, which is very interesting. This is saying that there's not much effect on the overall circulation pattern, which will then have not much effect on the overall ocean circulation pattern. But there is an effect on increased summer precipitation and seasonality over the region's highlands. So there's an effect on the precipitation, like you see higher seasonality and stronger rains during the summer as opposed to the winter. But the overall atmospheric, the wind patterns don't change much with the formation of the Himalayan Tibetan Plateau. And so they're just showing you have a little bit increased in summer precipitation. So you have a little bit more blue in these areas over the Himalayas, and that's the main effect of this topography. So the conclusion here is that the real driver of the formation, according to these simulations, was the emergence of the Arabian Peninsula, which was instrumental in the onset of upwelling off the Oman coast. And the Anatolia-Iran plateau uplift, it essentially deepened the low pressure area over the Arabian Peninsula, which then enhanced low-level wind intensity and moisture transport from the Arabian Sea towards the South Asian landmass. So stronger low pressure area due to the presence of the plateau, of the Anatolia-Iran plateau, and then that essentially just amplifies the wind intensity. So final caveats, this is something that they talked about at the end of the paper, but determining the timing of the true modern SAM depends on which metric you used, which that makes sense. If you look at atmospheric circulation and regional atmospheric ocean dynamics, which is pretty much what they're looking at here, that will tell you one story. Rainfall intensity would tell another story. So if you were looking only at rainfall intensity, then you would think, oh, okay, the formation of the Himalaya Tibetan Plateau, that's the key thing. But then if you look at the seasonal distribution of rainfall, and that would also kind of suggest the Himalaya Tibetan Plateau, that's also the key driver. So these 3 metrics are not controlled by the same factors, and they may develop independent of one another. So I think what the main conclusion here is that you have to look at all the different forms of evidence, particularly ones that you can perturb in a controlled setting like a simulation, and then try to reconcile that with some of the observations that they see from all the other different monsoon proxies. So that is it, and we can start discussing this now.
Okay, thank you, Bryan, for leading the discussion. And now questions. Anyone can feel free to have a question.
Hi, Bryan.
Yes. Are you in front?
Yeah, Yes. Thank you very much for the discussion. So, leading the discussion, it's a very interesting paper. Yeah, actually, I briefly read the paper, but I have to say I didn't understand much of the paper. But you gave a very good introduction, so I learned quite a bit from it. So I just found one figure interesting. So you show like I forgot which one is basically it's a kind of paleo geography or something.
Yeah.
Late Miocene.
But Brian, could you don't do the full screen mode, maybe, and add more? Yeah, I think that will be a good point to which slide.
One of your earlier slide showing the kind of comparison of
like this one.
Not this one, like a zoom in one. Maybe next one. Yeah. So I'm just wondering when you're talking about the upwelling, it's an upwelling of the ocean near the coastline, right?
Yes. Yeah.
I found like, for example,
upwelling.
the right figure show early Miocene. I found like the peninsula is actually submerged by the seawater.
Right.
So it's not like the rise of the sea level. It's just kind of dynamic thing, right?
Yeah, that was the configuration in the early Miocene. There just was no peninsula. So I think what they wanted to do was to take the late Miocene and then remove only the peninsula. So it's kind of like really pinpoint it down. Is it only because of the peninsula? Take away the peninsula and then see what the effect is. But I think that, like you're saying, the peninsula is the main difference between the late Miocene and early Miocene, just by comparing these two plots, these two maps.
Okay. Yeah.
But there's also the orogeny here.
Topography. Oh, yes.
Yeah, the topography. Yeah.
Okay. Did they also mention why they, when they run the simulation, I assume they have to assume certain, I don't know, like model or they especially chose that one. Did they mention like the reason why?
Yeah, that'll definitely be what one of the things I would like to ask her at Wednesday. Basically, what are the main sensitivities of different choices of the simulator? I don't know much about atmospheric dynamic simulations, but yeah.
So for example, like geodynamist, I spoke to Claire Curry from Alberta, right? And she's a very experienced geodynamist, and she doing all kind of like basospheric deformation modeling, this kind of thing. So I always ask him, like, how did you modify your model in order to get this kind of size observations? And sometimes once she told me, like, you can tell me what kind of result you want. So there's always a way to fine tune this parameter to get the model you want. So I don't know if they had the same, face the kind of same situations in their work.
Yeah.
When we have one atmosphere scientist in the room, you can ask an atmosphere scientist talk about it. Is that Shu Shoujun? Is that you? Could you open your mic and share your opinion?
Yes, thank you, Zhang Zhou. Thank you for Professor Bryan. I have one question. Have you done something for the East Asia monsoon?
Me personally, no.
East Asia monsoon. Because this work is about the South Asian monsoon from India to the South Himalaya. But for the East Asian monsoon from Australia to the East Asia, there is another monsoon circulation. So have you do something for the South Asian monsoon? I find the land sea around Australia is also different between late Miocene and the early
Oh, really?
Miocene.
Interesting. Yes, you're right. Yes. Yeah, that would be a very interesting question to ask the speaker on Wednesday. I think there are a lot of similar effects going on here. You have essentially a submersion of peninsulas, particularly in Southeast Asia. So do you see in the East Asian monsoon, are there strong differences between early Miocene and the late Miocene?
Yes, I guess the East Asian monsoon also differ between two periods. I think because the monsoon is triggered by the land-sea contrast. For the East monsoon is originate from is formed from the Australia. So if the Australia is changed, so I guess the circulation is different.
Yeah, I think there's probably some similarities there. So in terms of the atmospheric circulation models, I guess depending on, like you said, it's dependent on the land sea configuration. Are there strong dependencies on model configurations? Let's say topography resolution. Does that have a big impact on the modeled atmospheric wind speeds? Or are there other very strong boundary conditions that could really change the outcome of the simulations? These are my main questions. Like what are the things that you can change in the model outside of the land sea configuration that could have a strong impact on the simulation outputs?
Yes.
So are there any of the tips or tricks when atmosphere scientists, let's say, tuning these models? Basically that's also Bryan's question. I'm also curious about that.
Yeah.
Maybe you could give us one or two examples how to tune in the model to get a certain result. We don't know because we are not atmosphere scientists.
The model just is a public release, so everyone can use the model.
Yeah, but there are a lot of different parameters here using the model. So as Bryan mentioned earlier, that whether you tune in certain part of the parameters that could, let's say, for example, let's say you change this parameter, then you will change this result because we are not familiar with this model, so we don't know what's the correlation between input and output values.
Okay, maybe we can cooperate in the future to do something about the atmospheric circulation around the globe, also for the East Asia.
Yeah, I'm thinking my guess would be topography resolution, and how you parameterize air land drag, essentially. Just from what I've heard in seminars over the years, the resolution of the topography can have a big impact on on the simulation output. But I'm not sure how paleoclimate simulations differ from, let's say, projections, global circulation models for projecting over the 10, 20, 30 year period. Potentially, on the 1 to 2 million year time scale, that it all averages out. And the main factor is the actual distribution of land. So it could be that. We'll see. I guess we can ask on Wednesday.
Yeah, I think, Bryan, this is quite interesting thing because I remember last year we read that paper. Also, the speaker talked about it because they were talking about also using this kind of global climate models to say that
Yeah.
how does I say the biggest one of the biggest volcanic eruptions. I forgot at that time, maybe around 1 million years or something like that. How does that affect the global climate? And their conclusion is that okay, that affects some parts of the world, but not parts of the Africa, so that the Asian human sapiens that were not affected. So, but that actually, I'm not sure, but I highly suspect that that model didn't take any consideration of topography change because they use a modern atmosphere model that should have no way of knowing how to control.
Right. Yeah, thanks for reminding me. Yeah, they did also look at what would be the effect of a larger Antarctic ice sheet. Basically just means like the effect of cooler air temperatures globally. So that's a global effect. And how does that influence these regional simulations? And I think it's essentially a minimal impact, which is why I didn't put it in these slides, but I may have to look at that again. But yeah, I think, things that would affect the global climates at this time didn't have much strong impact on the formation of the South Asian monsoon. So I don't think, it seems to be like the key driver here is just the distribution of land. But, it's a good question for, what would happen in the future if, we have very different temperatures, how would the circulation pattern change?
Another one quick question. So did they just run a global simulation? Like they incorporate like the global landmass and consider, a sort of kind of distribution of I don't know, global paleo ocean geography?
I don't know.
To me, it sounds like a very extensive simulation if they consider the entire globe. Just to look at like the kind of regional scale.
But then you'd have to consider, okay, what are my boundary conditions if I'm looking only at this square? Periodic boundary conditions, that doesn't look good because between the left and right, that's probably not going to work. So maybe they extended it further, but yeah, I think you're right. A whole global simulation just to look at the South Asian monsoon sounds very expensive.
Yeah, well, the previous figure, like global distribution of the land sea area, are these figures cut from their paper or?
Oh yeah, these figures came from the actual model itself.
Slide 8. Like, okay.
Yeah, slide 6. Yeah, these came from the modeling paper. So I don't know. Yeah, my bet, I would think it'd be hard to isolate, a fairly limited region, just because of the boundary conditions would be very weird, considering you have atmospheric circulation. But who knows? We'll see.
Yeah, but in slide 8, right? They did show like global distribution of land, the topography.
Yes. Yeah.
So I assume that's probably what they input to the
it's what they input. Yeah.
Okay.
I don't know, maybe they got this from another paper, but.
Okay, I have another question. That in one of your slide showing that they have 3 scenarios. One is with a higher topography of the Himalayas. I think.
Oh, Himalayas. Okay. Yes.
So
slide 20.
Okay, but that sounds very counterintuitive. How could you have a higher Himalayan topography than today? Because let's say Himalaya is constantly under rising because Indian plate.
Right. Yeah, I don't know. My guess is that they're taking this effect of including the Himalayan Tibetan plateau and just basically cranking it up even higher, just to see what the effect is. That's my intuitive guess. But I I might have missed it, but they didn't really give a full explanation of why they went with this third configuration. It's basically, I guess, just exploring the model space a little bit more, just crank it up even higher, and see that.
Okay, so they are doing 3 scenarios independently. So they ran model 3.
Yes. Yeah, I'm also surprised that it didn't have that much of an effect on the circulation patterns.
Okay, thanks so much for today. It's an interesting one. Let's see Wednesday. I hope that more atmosphere scientists will show up on Wednesday and hear their opinions. But
clear things
also
up.
from reading this paper linked by you, that I have feeling that atmosphere science doesn't know atmosphere like very accurately. So pretty much we're still in a similar scale for geology and atmosphere scientists to a certain extent, especially when I'm talking about the paleo or something, and a lot of things that when I say not when out of bounds, but it's let's say are less well known, or people doesn't consider that thoroughly, I would say. But interesting. It is interesting to learn more about atmosphere science. Okay.
Yeah.
Okay. Thank you, Brian, for the discussion. Thanks everyone for participation. Then I'll see you speak on Wednesday.
Yeah. See you on Wednesday.